Hi everybody. So I want to talk about energy. I'm sure we all have a sort of a good idea what energy is. Light can be energy, heat can be energy, things like that. But there are certain things you might have to know for the MCAT in specific reference to energy. So hopefully I can help out with that. So first off, I want to talk about like kinetic energy. So kinetic energy is denoted with the letter K. Pretty easy to remember, K for kinetic. And it's given by this formula. I'm sure a lot of us have seen it, half mv squared, right? That basically is just the formula for kinetic energy. It's good to remember that. You should remember it because like they might ask you questions. But this m stands for mass, this v stands for velocity. So it's half mv squared. This half is a constant, and you're gonna square the v for velocity. That being said, its units are, that half counts as a constant, so we don't really have to include that. It'd be kilograms times velocity, which is meters per second, but we're squaring that, so it's over, so we square both terms, right? So meters squared per second squared. But this is also referred to as a joule. So we can say that the SI unit for velocity is joules, but it's also kilogram meters squared per second squared. So that's that. Another thing I want to talk about is potential energy. Potential energy isn't as intuitive. We don't use a P for this, but we use a U. So P is generally like saved for like power, but U is also potential energy. Now potential energy has different types. You can have like chemical potential energy, you can have like gravitational potential energy, elastic potential energy. So basically a lot of what you're going to see referred to is like gravitational potential energy, and that's denoted by this formula, mgh, or you might see it as mgz, it just depends. But this is mass, this is the acceleration due to gravity, and this is like height. So you're going to find that a lot of times like potential energy is taken from like a datum, which is like a point where we can say that the potential energy is sort of like zero. So basically potential energy, the higher you get, the more potential energy you have, because you have the more chance to like release that energy when you're dropped, right? That's why like things have energy when they hit the ground, right? And they dissipate that energy. So for example, right, if I have like from here to here, right, I might take this to be my datum, and like this h now becomes my, like, the distance between here and here is like the h that I'm going to use for my potential energy. Then I multiply that by the mass times the gravity, and then I'm going to get my value for potential energy. A lot of the time you're going to see potential energy taken as a difference. So you're going to have like delta U, which would then be mg delta h, because these two are constants, right? This is the only thing that you have sort of a change in, right? Likewise, you can also have like elastic potential energy. So remember, so potential energy is like the capacity to, it's like the potential to like do work, right? So things like springs also have potential energy, and that, like a spring's potential energy is given by like half kx squared. And basically this is done like with like I said, springs. This k is like your spring constant, so it's just a measure of like how thick or how stiff rather the spring is. This x is like distance that the spring has. So like the distance the spring moves from like its rest point. So that's what that x is. And then again, you're gonna multiply those out. Same thing, joules. Let me see. We also have like an equation for total mechanical energy. So when we're dealing with mechanical energy, we can say that E, right? So E is what we use for like mechanical energy, sort of intuitive energy, right? E is equal to just the kinetic energy of a system plus the potential energy of a system. Pretty straightforward, right? Now there's something we have in like thermodynamics called the First Law of Thermodynamics, which talks about like the conservation of energy, right? So we then go on to say that like this is equal to, the change in this is equal to 0. So like delta E, if it's conserved, right, is equal to, let me do it all in blue. so that's sort of like your first law, sort of. This is just saying like that mechanical energy is always like it's conserved, right? And this is what we have like in situations where things are like perfect, right? There's no like loss of like energy in any type of way. So that change in total energy is going to be zero. I also want to talk about like non-conservative work. So basically, that is a situation in which like if it's zero, that's a situation in which like I said, it's a perfect condition. But like if like it's non-conservative, like if things like friction are taken into account, right? Then I can go ahead and say that the change in non-conservative work is equal to my change in kinetic energy plus my change in potential energy, right? So if my change in non-conservative work is zero, it's probably like a perfect world, right? But if it's not, then like this is how you can calculate the change in non-conservative work. Let me see if there's anything that I missed. Don't believe so. Yeah. So pretty straightforward. You can add these up to get like your total change in non-conservative work, which is also equal to like the total change in energy of a system, right? You just add them up together and everything. As always, if anything was unclear, please let me know in the comment section. Hopefully I can do my best to like sort of like let you know if this is how you go about like finding whatever answer. Please don't forget to like and subscribe, and let's keep learning, okay? Thanks.